because that's another busy room. Might be. Thank you.
Okay.
So I guess no one else is showing up here.
Here, probably, yeah, probably we have all people here, so we can just start. Yeah, I think so.
So I'm Siyang Li. I'm a PhD student at Imperial College London, supervised by Professor David Van Dyke and Dr. Max Alterent. So my presentation today is on the moment generating function methods in the estimations of the luminosity functions, where we have a cluster of potential X-ray sources, and where some of these X-ray sources could be dark. So here's the structure of my talk. I will first briefly introduce the astro-statistical problem, and then I will introduce a method based on moment generating functions that can simplify or speed up that is an analytical solution for some complicated computations, statistical computations in this statistical problem, and which can also be extended in various ways. That is not only useful for this particular statistical problem, but can also be applied in other areas of statistics, as listed here. So first, on the luminosity functions with the presence of dark sources, our main objective is to efficiently estimate the distribution of X-ray flux among the X-ray sources. And by efficiently, I mean we try to statistically marginalizing out or integrating out the intensity parameters of these X-ray sources. But there are a few challenges in this for this objective. So first is that there could be background contaminations to our observed photon counts in the source regions. And the second is that some X-ray sources could be dark, that we did not observe any X-ray photons from these sources during our duration of observation. And the third is that there could be overlaps between the source regions. And here I propose a moment generating function based method that could analytically solve all of these challenges in order to achieve our objective. And this is currently the only analytical method for this objective at this moment. So here is the main structure of our model. And as you can see, we have a hierarchical model. This is because there's a large number of X-ray sources, and so for each of the X-ray sources, we use an independent and identically distributed source intensity parameter, and then we assume that the number of photons from the source is a realization of this source intensity parameter, and that follows a Poisson distribution. And in particular, the source intensity is known as the risk-yield expected source count. Maybe like this risk-yield is to some physical sense, and
this just assumes point sources, right?
Sorry.
This just assumes point sources. So.
Yes. This is the relationship between the source-wise level of the models, where each of them have a Poisson likelihood. And there are also some key astronomical concepts and deterministic variables that we need to bear in mind. The first is the point spread function, and the value, the size of the point spread function will give us the radius of the source region, where approximately 90.
Just to follow up on Axel's question.
Yeah.
So the astronomy task here is to figure out the luminosity function of stars. Mm-hmm. And the particular data set that Siyang has been looking at is star cluster. So no, we haven't had a way of that.
Yeah. Okay. And can I just ask,
one thing that's always puzzled me a little bit, when you say, when we say luminosity, there's flux, is it luminosity?
Yeah.
And then there's counts, expected counts. Which is it that when we talk about luminosity?
So counts over the exposure time,
Yeah.
you see count rate,
Yeah,
which can be converted to a flux at the telescope.
yeah, flux is total energy.
No, flux is
In the
count
aperture.
ergs per second per centimeter squared.
Yeah, but the per centimeter squared is the
Is
part that
at-
makes it not total.
Well, what do
So I
you
was
mean by?
reading about this, there's like you have a star, it's generating energy in all directions. And I thought the flux was the part that's passing like a per centimeter squared radius or
Yes,
area.
but yes,
Yeah.
but the trick,
Aperture.
but the problem here is that we measure things at the telescope aperture.
Yeah,
So, and the star is a point
far away,
source.
yeah.
So it is, yes, so the per centimeter square at the telescope, the ergs per second, that's possible.
So it's
Ergs are
energy,
possible.
sort of energy
Yeah.
per area.
And so, but you could imagine trying to correct for the distance of the stars
That's
for the
what
reason.
That's,
luminosity.
that is the luminosity.
I see. And you could also, because I think we're looking at Poisson models for the counts.
Yeah.
And counts, if they all have the same spectrum, all the sources have the same spectrum, then there's
The conversion is straightforward.
it's proportional.
Yeah.
So what we're doing is maybe, I mean, we could say we're assuming they're all the same distance or approximating them. Maybe it's because they're a cluster, that's probably not so far off. But do we also, because they're all stars, assume they have more or less the same spectrum?
More or less the same spectrum, but this leads into the, was it Max or was it Vasilios who was doing the hardness ratio correction to the luminosity?
I see. So I know
So that
was
is where you can make adjustments to the conversion factor and
based on a
Based on-
rough measure of the spectrum. Because this all came from, I was looking on Max's paper with him and how we talk, like there's this talk about the conversion factor. It sounds like it's like a simple conversion factor, we don't have to worry about it. But
not
that's
like
under an assumption about the spectrum, and maybe we can worry about it a little bit by hardness ratios.
Yeah.
I see, okay.
And also there is an assumption that the volume is all the same, right? When you do the surface on which,
Well, I mean, this
Because
is
it is
a star
centimeter.
cluster, so
Yeah.
it's limited in
yeah,
distance.
but I'm
variation.
talking about luminosity conversion, there is,
Oh, yeah, yeah,
for
I mean,
pi
yes,
d
when you start
squared,
getting
so,
into
yeah.
extra galactic sources,
yeah.
even just field stars in the galaxy or something, then.
Yeah, you
yes,
always
not-
assume that they emit the same in all directions.
Yeah.
So whatever you observe here, it's just
It's proportional.
Oh, yeah, that too.
But does the distance distribution matter here? Like, I mean, it depends on like what,
It should not.
it depends on
but-
what you look at, right? I mean, my background is, or I've done similar studies on sources in the galactic plane, and there matters, right?
Yeah, I mean, if it were a
Like
globular cluster, it
yeah.
would definitely matter.
Yeah.
But there's an open cluster, so less.
Relatively
So it
small,
depends on the source.
but also relatively closer.
Yeah.
So the
well,
relative distance might still be kind of similar.
Yeah, I mean, the change in the distance between the front of the cluster and the back of the cluster is
We don't worry about
minuscule.
it. Sorry.
Yeah, thanks for all these discussions. I didn't know all these details.
So at some point, when you write a paper, we have to say what, you have the distribution of the lambdas, and we need
Yes.
to make some connection between that and the science, and that's what this is discussion.
Yeah.
Yes, nice, thanks. So, yeah, and there are other, like, the luminosity function is also needed here, which I think because most of these definitions are from Nagi's previous paper, so which was unpublished. So here it was defined as the distribution of the source intensities in the population, and we also need the area of the source region within the unit of pixels, the exposure time for the pure background, and the source observations in the unit of seconds, the proportion of photons from the source that are expected to fall inside the source region, which is assumed to be 90% here at this moment, the telescope effective area in the source rotation,
For
which
an isolated source.
Oh yes, for isolated sources. Yes, yes.
Not
Yeah, that's why I say it's at this moment because later on, yeah, yes, and also the telescope effective area in the source location in the unit of centimeters squared, the area at which the background count, the pure background count is collected in the area of pixels, and also we need information on the location of the sources.
So this is something that I also was puzzled by. Because because we were talking about this in my email.
Yeah.
Originally, he has the areas that correspond to the source in centimeters squared, and the areas that correspond to the background in pixels.
The effective area was centimeters squared.
Yeah.
The area is also pixels.
The size, yeah.
So the little a,
Little
where's the effective area?
Don't know.
E. Yeah.
I see. But that little a, that's, I mean, okay, so little a is for background, okay, not that, right?
Little is for the source region, the area of the source region.
But look at your model, it's a times c.
A times C, yeah, that's the background contribution to our observations.
Yeah. But why do we use, so that means that c is somehow counts per pixel and lambda is counts per centimeter squared.
Well,
No, C is what is C?
What is C?
C is the background intensity parameter.
Oh, okay. So the counts that you observe within a source region
Yeah.
includes the contribution from the source itself.
Yeah.
And the flat, assumed to be flat background.
Yeah,
Right, so that is the A times C.
yeah,
Plus R is the fraction of the PSF.
yeah.
Times
yes.
Oh yes, why do you have an effective area? Oh, E times lambda is
Yeah.
counts, is the estimate. Lambda then is in photons per second per second.
There's, R is a proportion, it has no unit.
R has no units, but E times lambda times T is photons.
But shouldn't a and little e have the same units and c and lambda have the same units?
I guess the two
No.
reads have different units.
Okay.
No, because regardless of how big your source circle is,
Yeah,
you assume the source is contributing to the whole thing. So the area does not matter except for the
for
R.
lambda. So,
Except for the R.
so a having unit area pixels.
Yeah.
And e having unit centimeter squared.
They're different things.
Yeah, but does that make sense?
Yeah.
Okay, sorry.
Yeah. I mean, in the sense of so C and lambda don't have the same units. C is counts per centimeters, counts per pixel. So
Yeah.
that's the background rate.
And what's lambda?
Lambda, it
Just
looks
total
like it is
count.
photons per second per centimeter.
Yeah, so I guess it's just strange to me that we use per centimeter squared for one and per pixel for the other, but that's what you think we should do.
As long as it balances out, doesn't matter.
Also in general, I mean, for example, for gamma ray telescopes, the effective area for signal counts is not the same as for background.
Yeah.
Yeah.
So because like there's
Really?
this process, yes, yeah.
It's different.
No, even for
And
X-rays.
even maybe for X-rays, there's maybe like an instrumental background or something like this, and then the effective area is in fact different.
Yeah.
So yeah.
So it's good that we split out the EI away from outside of the background. The background is being
Yeah.
treated completely phenomenological,
Separately. Okay, sorry.
empirical.
So just for me to learn, after working on this project for 20 years.
Is it 20 years?
What's his name? The Greek guy?
Vasilios?
No,
No,
not that.
not this.
Roundas, oh no, Roundas are actually.
There's the problem of the background contamination of our observations. This is because the universe is three-dimensional, but we only observe it through the telescope, which gives us a two-dimensional images. Which means that the X-ray photons from the background would contaminate the photons from our interested sources. So, which means that our observed number of photons in each source region would have some contaminations from the background that we don't know how many. So, which means that we do not have direct information on the source count, but we only have a contaminated one that has, and we do not know we do not have direct information on the background count per source region as well. So, but the previous approach is to use a background subtraction, which is to simply subtract an estimated number of background counts from each source region. But when the source itself is faint and the background is strong, this could lead to negative estimates to the number of source photons, which is not physically possible. So here we use a new approach, which is to consider the background intensity parameter, and so that the
Well, strictly speaking, it's not new. I mean, we
Well,
did this in 2001 at least.
Even Laredo,
Yes.
1990.
well, in Large's paper, it was.
So this is for this case.
For this case.
For this case. Yeah. So, now we have a background intensity parameter, and then the background count per source region would simply be the latent variables in our models. That's not directly observable, but we can leave it there. So the model structure is like this. And also another issue is that there could be some X-ray sources that are X-ray dark, in the sense that in our duration of observation, we did not detect any X-ray photons from it. This could be because that the source itself only emits optical light and it's intrinsically X-ray dark, or that we just didn't observe it for long enough such that if there are loads of such sources stacked one on each other, we could detect some of the X-ray photons in the same duration of observation. But for the same duration of observation, if we only detect one of these, if we only look at one of such a source, then we just couldn't see the X-ray photons arriving at the detector. So to resolve this challenge, we use the zero-inflated gamma distributions as the population distributions for the source intensity parameters, such that it has a strictly positive probability for the source intensity parameter to be zero. And so this is how the zero-inflated gamma distribution looks like. And we introduce a new parameter that corresponds to the proportion or probability for the source intensity parameter to be zero. And another challenge is that the source regions could overlap with each other. So, and within this segment of overlaps, the X-ray photons that arrives at the detector does not come with labels saying that I'm from this source or I'm from that source. So not only the data is background contaminated, but also the data are contaminating them with each other, with themselves. So so to deal with this challenge, we reformulate or modified our likelihood such that now we don't consider the source intensities, but we consider the segment intensities. That is the X-ray intensity that would correspond to each segment that's being cut by all these overlaps. We consider the segment intensity parameters, and we also need to make a few adjustments to the other deterministic variables, including the area of the segment, the effective area, the telescopic effective area of the segment, and also the expected proportion from each source to the segment, the particular segment.
Can I ask you a couple of questions?
Yes, sure.
So for the zero-inflated gamma distribution, how would you pick pi d?
Well, we don't pick pi d, but we estimate pi d. So like we put, I think we could in Large's paper, which was a few years ago, she used the beta prior distribution on the for the parameter pi d, and then just put it in the likelihood and get an inference about it.
Okay.
Yeah.
And then my other question was, also was asking about whether the sources were point sources, but now when you're talking about the segments, like the segments of the overlap between the source regions,
Yes.
then how are those sizes set? How many pixels are typically in each of these segments?
I was about to comment on that. These overlaps that you find are based on the optical locations. So,
Oh, okay, so that's not necessary.
so that is, I mean, you got detected X-ray sources, which are
Okay.
generally well isolated, plus what we believe are known sources from an optical catalog.
Okay.
So you stick the optical, if you go to the first plot that you had,
First.
yeah, page
The
one.
very beginning,
The
Max was wrong.
sources, all the sources.
Yeah,
this
that one. Yeah, I think the blue are all the optical sources.
I see that.
And yellow
And,
circles.
so there is no issue with overlaps for the X-ray detection sources.
Okay,
Because
but,
if they're too close, then they're.
You could detect them both, yeah.
okay, sounds good, thank you.
One more question on the gamma distribution. Is there a physical motivation to use it? I assume, I mean, there might be, I mean, like a lower cutoff to the luminosity, I guess makes sense. I mean, there might be some kind of threshold. But typically, I mean, you also often see like that they're typically more like power law shape and the weak sources.
Yeah,
But
I mean,
physically, at some point, I guess you expect a cutoff. There might be some sources.
we picked a gamma only because it was very flexible. And the idea of the zero-inflated or a dark population is simply that there may be, if you know, everyone assumes that the luminosity function is unimodal, but it's not necessarily so. If there is a second mode below some exposure threshold or something, you would not see it. And this is sort of expected for stars, where you might have two populations where the rotation Cecilia's work, right? You remember what Cecilia is working on with this rotation activity evolution. It leads to a bimodal distribution of the counters, of the luminosities. And we would not expect to see a population which has already decayed in luminosity. And that might all be absorbed in the zero. So
Yeah, so
it's
kind of like
unclear
treat,
if
you treat it as two classes, right? So it's either
at least two.
detected or like non-detected.
So we are trying to model, you know, it's possible that that using a gamma distribution, a unimodal gamma is not necessarily the best thing for a stellar luminosity function, but no one knows like that.
I have some more words on the choice of gamma. It was chosen for the motivation was analytical when gamma was chosen in largest paper, and but all the methods that I introduced here could also work with other population distributions such as broken power law distributions. So yeah, it's easy. It can be easily replaced by broken power law distributions.
Is that, your moment generating function methods all work?
Yes.
You figure out all the derivatives and everything?
No, I didn't even figure out the exact form of the derivatives for gammas either, but I know it works. If it works for gamma, yeah.
How do you know it works?
If it works for gamma, I mean,
You don't know it works
because
for
the
gamma either,
philosophy-
okay.
Because the philosophy is the same. The lines of calculations are the same.
Yeah, but it's not a question of philosophy.
Yeah.
Right.
So yeah, this is the likelihood that's adjusted for the overlaps, and if we consider the segment intensities and segment counts rather than source counts. Note that here we have a summation of all the source contributions for this specific segment S, and plus a single background parameter for this segment. Yeah. So as in summary, because there's a large number of IID X-ray sources, we use a Bayesian hierarchical model because and to cope with the background contamination in our observations, we use the background intensity parameter C, and because of the dark sources that could be present in the population, we use a zero-inflated population distribution for the intensity parameters. And to deal with the overlapping source regions, we modify our likelihood functions. And here is a deck that summarizes this model. As you can see, here is the main part of the hierarchical structure, and here is the background contamination part. And that
What's the DAG?
DAG directed acyclical graph. Yes.
Okay.
So the arrows all go in one direction,
Yes.
and you can't come back on yourself.
Yes.
Direction.
I don't know why I guess in graph theory that matters, but for these models, I mean, first of all, the fact that it's directed makes no sense. Because if X is correlated with Y, well, you know what? Y is correlated with X. But somehow statisticians have gotten, I don't know why people make these plots, these things. I don't know. Somehow they think it's easier to understand the model, I
Yeah,
guess. I don't
I
know.
think so.
I guess it's more to depict the dependency relationship.
It's not
like-
dependency.
no.
If X, I'll say it again, if X is correlated with Y, Y is correlated with X, and these are not causal relationships, they are correlations.
Yeah.
You
but-
could just take all the arrows and draw them in the other direction, it would be no more or less meaningful than this. Right. I mean, it's nothing personal, I mean, but I mean, this is, I've been venting about
But
these,
usually
use of
we
these things
yeah, usually
in
we would-
statistics for, no one listens to me.
usually we will think about the number of photon counts that depends on the source intensities rather than the source intensity depend. But
No, but the
anyway,
B and the S
correlations,
are,
yeah.
you can split the B and the S depending on the data, right? So
Yeah.
you can put more stuff in S versus B. So there should be an arrow in between those two.
In the
Between
bottom.
which two, sorry?
No,
The background counts and the source counts.
I guess they combine like
Yeah.
in a convolution way or like in a summation ways like this. So yeah. So
Well, I mean, you should
This
be able
is
to
what we observe.
figure out conditional dependencies, and so I don't know.
Because yeah, it depends one on the other, and we don't know background precisely.
Yeah, I know, but like, what is it, why should there or should there not be an arrow there? There must be some reason.
Or between the two, background and source count.
Yeah, I mean, given Y, B and S are not independent.
Right, they are dependent on each other. Yeah.
yeah, that could be.
There should be one little circle.
Yeah.
Then it's not a deck anymore. But
Yeah.
yeah. Anyways.
But you don't use this thing, right?
It's
You
just
use the models.
Yeah, this is for presentation purposes.
yeah. So you can combine kind of, but yeah.
Can
Okay.
I just ask on the
Yeah.
overlap of the source regions
Yeah.
again, basically extending on what you've asked. So do you assume a spatial distribution, or do you just take the spatial distribution from the optical measurements? Right. I mean, if you assume, for example, it's a globular cluster, and as it's like integrated line of sight, like the density in the middle is much higher.
No, we use an actual catalog.
Use an actual catalog.
So we
And
know
this
that-
is what you, okay.
The
yeah, so you-
location.
Yes. And this is where you get your spatial distribution.
Yeah, yeah.
Oh, also, I realized we didn't answer Justin's question about where we get the radii from. That's from the expected, if there were a source at that location, what would the BSF size be
It's the X-ray point spread function at that location.
of the optical source?
Okay, so the position, like in your graph showing the circles, the positions of the circles are set by the optical catalog, but the size of them is set by the X-ray PSF? Yeah.
Yes.
And does the size vary with position?
Yeah.
Yes.
Because that's where we're gonna be looking at the X-rays to decide how far the source
Sounds
is.
good.
But there's a computational issue here that the dimension of the parameter space is like in the hierarchical model, even without overlaps, is larger than the number of sources, such that we have one source intensity parameter corresponding to one source, and there's also the hyperparameters for, or like the population parameters for these intensity parameters. So and if we consider the overlaps as the number of X-ray sources increase, there could be a lot more parameters in the parameter space, which is not statistically efficient, or and it's better for us to marginalize them or integrate them out, so that we can first only infer on the parameters in the population distribution, and then like after this integration, we can first only infer on the mean and the variance and the proportion of the dark sources here, and after inferring on these three parameters, if we would like any information on any specific intensity parameter, we can then maybe do a sampler or just do later steps. So yeah, we would like to do this integral, and we propose the method of moment generating function, which is the only analytical method to cope with all the challenges that I described above at this moment. So so here now the parameters are like, the notation is slightly different, but that's why I added underlines to underscores to some previous parameters for the X-ray in the X-ray models. So here the first formula, like here C denotes the hyperparameters, theta denotes the parameters, and Y denotes the observations.
So
and
just to be clear, C are the hyperparameters or the lambdas in this case?
Yes, the
Individual lambdas.
yes,
No, is it that the thetas?
yes, well,
It's got to be one or the other.
theta x like the hyperparameters, just like the
He said
mu.
lambda. Lambda are individual, there's a lambda for each object. Isn't that the theta?
This is, I thought it's C. Sorry, I was thinking these correspond to C, and this corresponds to lambda, and this
Well, the
corresponds
lambda
to
corresponds to theta. Lambda, that is lambda.
Yes, lambda corresponds to
Okay,
theta,
so-
and this corresponds to C.
So
Yes.
what you're calling hyperparameters are the description
Population
of the luminosity function.
Yes,
The
yes.
finite dimensional parameter,
No.
like the one that doesn't grow with the data size, yeah.
Go away.
Just move it away. What is it? Who
Close it.
cares?
Java update.
Oh, no, just remind me later.
Remind me
Skip this
bigger.
then.
Anyway. Okay. So the Bayes formula that includes both the parameters and hyperparameters looks like the first line here, and by the law of total probabilities, we can integrate out the parameters and only left with the hyperparameters in the likelihood, although this is not a likelihood function. And if we combine the first two lines, we can get another Bayes formula that directly infers the hyperparameters without needing to needing the information on the parameters. That's what we define as the statistical marginalization, that we integrate out some parameters in the parameter space and leave maybe zero or like one or two of a few of others, and we do inference on we can do inference on the remaining parameters first, and then we can come back to the parameters integrated out
Right,
later.
because that's a much better behaved statistical object, because the dimension of y, you can imagine the data set growing,
Yes.
and C stays the same.
Yeah,
So that's a much more standard kind of problem.
this is the magic.
That's the magic.
Yes. Okay. So the moment generating function method is based on three facts that I guess I think let me just briefly mention it. Here, let me take the Poisson likelihoods. This is the Poisson density, and also that's the high order derivative of an exponential function looks like this, and also the definition of moment generating functions, which is awfully similar to Laplace transforms for physicists.
Maybe you can just say why it's called a moment generating function.
Yeah.
because it generates moments by differentiations or by Taylor expansions or.
Right, but the standard thing is you take a derivative of that, the first derivative of that thing.
Gives the first, evaluate at 0.
At t equal to 0, right?
Yeah.
Just say it clearly, right?
Okay.
The first derivative of that thing with respect to t evaluated at t equal to 0 equals the expected value. Is that right?
And yes, and also we could do it by Taylor expansion.
No, just say clearly what it means.
Okay.
The second derivative
Oh, yeah,
And,
this is, yeah.
with respect to t evaluated at t0 is the expected value of what's the random variable? Theta squared.
Yes.
So you can generate moments, so it's called the moment generating function, right? Yeah.
So and we, based on these 3 ingredients, we can cook the most basic, version of the gamma likelihood moment generating function statistical marginalization theorem. And so here, first we realized that the marginalization integral, which was the last integral I showed here, is effectively the same integral.
What you want.
Is a prior expectation of the likelihood. Although this is not a likelihood function, but it's the likelihood, and I call it likelihood. So and here, because we assume it's Poisson likelihood, we substitute the Poisson density, or the form of the likelihood, and then we take out the parts that's not relevant to the theta parameter, and then we realize what's the remaining part is simply a high order derivative of the exponential function here, and then here we can swap the expectation and derivative, although it's linear, but it also assumes other conditions, and I've checked, you can trust me, and now we realize that it's a derivative, high order derivative of an expectation with respect to an exponential function, and this last part, the expectation of an exponential function, gives us a moment generating function, but it's the prior moment generating function to be specific. So, which means that we can evaluate this integral by this marginalization integral by simply taking the high order derivative of the prior moment generating function.
Right, and the trick is high order means that it's the order of the derivative is the number of counts. Right, so it's a pretty high, it can be a very high order derivative, right?
Yes, exactly.
So when you say generating, it means you just do these derivatives, first, second, and go on. And how many do you do?
Well,
why is the number of counts? So
So it's as many as counts.
It could be a lot of them.
Yeah.
Yes, so it would be ideal if there are eigenfunctions to these derivatives, so that we can work out a general form of whatever order the derivative is.
Right, and so this is what we were talking about earlier, right? Because theta given c at the very top, that's what we had as a gamma distribution, but we were saying maybe it should be a power law. And it's the moment generating function of that distribution, right?
Yes.
So, yeah, but just clearly, gamma distribution, power law, that's the distribution. And so that's why I was asking you the question, right? You said you have the moment generating function for either of those distributions.
Yes.
And you can take arbitrarily many derivatives of them.
Yes.
Easily.
Yes.
Just like automatically.
Yes.
You don't actually have to take all of the derivatives. There's a recursive formula that you can identify.
Yes, hopefully or usually that's the case.
No, but there's 2 distributions we're talking about, gamma and power law.
Yes, gamma is quite easy, and power law, it could be slightly harder and more complicated, but it's also possible.
Because you'd like to not actually have to take 1,000 derivatives, right?
Yes.
Like to recognize a pattern.
Siyang, can you hear me?
Yes.
Right. Now, you derive all these beautifully through mathematics, and obviously we want to understand what's going on, right? I'm a strong believer there's no coincidence in mathematics, right? It is telling us something. Okay, so here's my train of thought. And I need Anita's help as well.
Okay.
The moment general function is just Laplace transform.
Yes, yes.
Now, what is the physical meaning of Laplace transform? We know the physical meaning of the Fourier transform, right? Or the
Yes.
phase or the frequency. What is the Laplace? What is the meaning of the Laplace transform?
It corresponds
These
to the
These derivatives are simply like once you have the transform, derivatives are like Taylor expansion. It's just tell you like to which order coefficient matters.
yes,
And
yes.
so it is seeking that particular coefficiency. It's now if you think about in the frequency domain, sorry, in the Fourier transform, you're thinking about, if you pick up a particular coefficient, then that is picking up a particular, period, right? Periodicity, particular phase, right? Things of that nature. I wonder if there's something is telling you that if you have this much observation, then you need to look in. The evidence is like this much. There gotta be some physical interpretation of the thing.
I do have
Yeah, no,
I do have some probabilistic interpretations now, though,
Okay.
that I mean, it's in one of the later slides, but I guess I can just briefly
We can
describe
wait.
it
If
here
it's
as well.
yeah,
So
we can wait. We
yes,
can wait.
yes, okay, yeah, okay. It's about renewals and random stopping times, and that's that's heavily related to Laplace transforms in this stochastic analysis. So, and it's all related to here as well. And the random stopping time models have a coincidence mathematical structure with the surprisingly coincident mathematical structure with the Bayesian models as well. So, yeah.
I see.
Yeah.
okay. I don't know immediately what it would be,
No.
so we can wait for
Yeah,
Siyang
that's in one of the extensions.
yeah, so we'll see, because right now I don't know the Laplace
Okay.
interpretation.
So yeah, so this is the general theorem for the Poisson likelihoods, because previously we only assumed that there's only one observation and one parameter, but there could be like n parameters and each one corresponds to one Poisson observation, and this would be the theorem that can do the statistical marginalization for such a case.
Right, so just again, to make it clear, so this, if you had non-overlapping sources, this would essentially be what you need.
Yes, yes, exactly. This is because for non-overlapping sources, it's exactly one independent source intensity parameter that corresponds to one source count. That's exactly what this theorem corresponds to. So yeah. But when there are overlaps between the source regions, we now have the segment intensities rather than the source intensities, which the segment intensities can be considered as linear combinations of the source intensities, where the matrix here, the linear combination relationship here can contain would have the entry of 0 if that source region does not contribute to this segment, and would be positive if that source contributes some to this segment. Yeah. So so this result is what we need when there are overlapping regions. So when there are overlapping source regions, such that now we have the linear relationship R here, like scattering around in this in this high order derivatives, and also we can also have an offset parameter.
Can I ask a quick question, going back to what you said before with isolated sources?
Yes.
Max is doing his analysis with only X-ray data, only X-ray sources, right? Log and log S.
He has optical locations, so I mean, it's just like this.
But is he using those, or is he using the?
Now he is using Gibbs sampler.
No. I mean, is he using the optical?
Yeah, he has two. He has the X-ray luminosity function and the optical luminosity function. Remember? So that in fact, you don't. I'm saying luminosity functions. Incompleteness functions. You don't have incompleteness functions. these, they're kind of addressing different things, right? There's no incompleteness, you never talk about incompleteness function, right? Whereas that's
No,
Max's.
you wouldn't need that because, I mean, each of these is an individual estimate for each source, right? And you're marginalizing them.
Sure, but if you want to know about the distribution of sources, not the
Then you
distribution of
need them.
observed sources, then you would need that. So Max is using the incompleteness functions, optical data and X-ray data, and both of the incompleteness functions.
Okay.
But yeah, and he's not using it as MGF stuff, he's using old-fashioned Gibbs samplers, but there is no overlap. So you haven't quite got to the punchline at the very bottom there. But that makes the overlap really is why you need to do this.
Okay, that's simple.
Yeah, that.
Yes, yes. So, well, there's an example that follows this slide that shows the.
Well, maybe you can just say though. So if they're isolated, you can do the integral in closed form. It's just
you
an
can
integral.
separate the integrals. Like you can, it's a
One-dimensional integral.
It's a product of one-dimensional integrals.
And if it's a gamma Poisson, the integral standard year one undergraduate problem.
Yeah, that,
If it's negative, we call it power law, that's no longer the case, but at least it's still one-dimensional integral.
yes, yes.
Just have to do it very
Product of
numerically or
one-dimensional
something, or
integrals.
approximately. But if you have the overlap, all of that, there is no analytical solution.
Apart from this method.
Yeah, I'm sorry, apart from this method.
Yeah, so at this moment, at least for that I'm aware. So,
Yeah.
So,
And that R, just to be clear, that R is a matrix, it just maps the individual source intensities to the
segment
intensities,
So
right?
it's theta.
And that's a linear transformation.
yes, that needs to be a linear transformation. Otherwise, this method could also fail.
Yeah, okay.
And yeah, so here's a simple example that demonstrates how this demonstrates the usefulness of this analytical method in the case of overlapping source regions. Here we assume that there are 3 source regions and that they overlap in such a way and that we observe the photon count in each segment as 0, 1, 0, 2, and 3. And that the contribution from each source to the segment is given by this matrix, where the 3 columns correspond to the 3 sources, and the 5 rows correspond to the 5 segments. That, for example, the first source would contribute to 0.1 of the photon count to the first segment, which is 0 here, and etc., etc. So this problem is basically what.
Wait, sorry.
Yep.
Why is it 0.1 and shouldn't that be 0.9 and 0.1?
Well, it's assumed to be this. Like, I mean, these are this.
You've got a larger area.
Yeah,
This
not to
plot is.
scale.
You can
Oh, it's
see
not to
this.
scale. Okay,
well,
sorry.
Yes. Yeah, I should add that this plot is not to scale, but that looks. It's more.
You have to, I mean, it's a bit extreme, you have to think if we could actually make it plot to scale, but if you imagine that the 90% of lambda 1 is in the overlap and 10% is outside the overlap, is what he's writing.
Yeah.
Yes, so yeah, exactly. I should mention that this plot is not to scale, but this idea is the same for the in the analysis for the true X-ray data. So this model is equivalent to a Poisson identity link random effect generalized linear model with no fixed effects, by the way, but this is not important. The important part is that we, using the moment generating function method, we can analytically calculate an exact value for this observation to be true, given that given the value of the hyperparameters, where here we assume that the source intensities, the lambda 1, lambda 2, lambda 3, follow IID gamma distribution of shape 4.5 and rate 2. So we can analytically calculate this probability, and currently there's no analytical methods that I know that can do the same job. But
So you're computing the probabilities.
Yes.
That's an available analytic.
roughly?
That's the, well, it's given, it's only given the hyperparameters. It's not given the parameter values, and that's, this would, this would involve the same issue like integrating of the overlapping, yes.
Yeah, that makes sense, yeah.
Yes, so, we did a whole lot of iterations as a simulation to such that we simulate using this shape of 4.4, gamma shape of 4.5 and gamma rate of 2, we simulate the three source intensity parameters, and we then linearly combine these three source intensity parameters using this matrix A, and then using the segment, the result of the linear combination as the segment intensities to simulate, as a rate of Poisson to simulate the observations. And we try to see how many of these simulation iterations match with our assumption, which is 0, 1, 0, 2, and 3. And it's this number, it's 5,694 iterations that match with this. On the other hand, we can do a hypothesis testing such that we can set the null hypothesis to be that our analytical derivation is true, and then the null distribution would be a binomial distribution where the total number of trials is our total number of iterations, and the success probability is our analytically calculated probability, so we can get a central magnified credible interval for our for the number of the success iterations that's consistent with this null distribution, which indeed includes our number of success iterations. So which means that the computer simulation is consistent with our analytical calculation to this problem.
Right, so analytical was the second
was
one.
this one.
This one, yeah,
Yes.
okay. And this is...
And this many iterations
So,
are successful.
so the P is exactly the same to like whatever, 8 numbers, 9 numbers?
Yes,
5, 6, no,
yes, this is...
that's an analytical calculation, so that's,
Yes.
you can kind of do it.
I can,
Oh,
if it's,
okay,
if
and
it's
then
like,
you got this...
if it's a fraction, I just enter the fraction in the code.
But the 5694
Yeah,
is,
it's the
that's from
one
Monte
model,
Carlo, yeah.
yeah.
Yes.
Okay.
Yeah, that's probably fine, that's Monte Carlo. It's probably better to try to get to the stuff that Siyang Li would be interested in about that.
But yeah.
Yeah.
Anyways,
Can you just go back to the overlap illustration?
Picture, yeah.
Yeah, so you count the events in the overlap regions independently. This is what I get from this. So you assume.
You get the count in each of those little
Yes.
overlap regions, yeah.
yes, yes.
Okay. And this way, I mean, could you handle like triple overlaps?
Yes, yes, that's possible.
It's
Although
just-
the mathematics is a bit more complicated, that's why.
The mathematics and the bookkeeping. Like if you think about dealing with the data set, it becomes a lot of trouble.
Yes.
But
Anyways, so yeah, it's simple enough, but there's also 3 sources. That's why I constructed it like this. And the similar results also holds for gamma likelihoods. Following the same steps as for the Poisson likelihoods, we can also arrive at similar results for gamma likelihoods, except the difference here is that we use Riemann-Liouville fractional derivative with a lower limit at negative infinity, rather than an integer order derivative here. This is because now the order of derivative is determined by the shape parameter in the gamma likelihood, which is assumed to be known here, and that this shape parameter does not necessarily need to be an integer. So yeah, similar results hold for gamma, and this is for univariate gamma with assuming only one observation.
just, again, just for the astronomers to make sure everyone, Poisson is the counts, that's non-negotiable. And then you have with the distribution of the sources gamma or power law. Now he's looking at the non-negotiable part for thinking about how this would work outside of the problem.
This will be for a different problem that has a gamma likelihood.
Almost certainly outside of astronomy.
Yeah.
But it does come to these interesting, weird fractional derivatives, right? So the mathematics is kind of fun, but
Yes.
I mean, in gamma likelihoods are a little unusual anywhere, actually. But they're not unheard of. So.
Yeah, it's in. Sorry.
Yeah.
Yeah.
Can you hear me?
Yes. Yes.
The fractional derivative in general is actually integration, right?
Yes.
So
Yes.
there's no really saving.
Yes.
I-
There's. Yes, you are right. Yes. Although you can imagine that there could be some computer programs that already have the fractional derivative. For example, maybe MATLAB or other programs that have the fractional derivative operator, and you just enter the operator and give you the expression. Yes.
The way it operates will be just doing the same program can do numerical integration because it's
Yes, I mean yes. Okay,
it's a same
and
thing. But
also
what I'm getting at here is the how bad it is, can you derive bounds? Let's say I just use the nearest integer of alpha, right?
yes.
Up and low. Is there some bounds? Like, if it's in between these two alphas, is there anything you can, for practical purpose, it's not as good as the exact, but still, whether something can be done.
exactly. I mean,
More integration.
we conducted a cake baking example to
We didn't conduct it.
no. I mean, the analysis. We conducted the analysis of a cake baking example to demonstrate the usefulness of the gamma theorem. And in that example, we indeed assumed that the alpha, the shape parameter, takes the parameter space of integers rather than.
So whose paper was that? David Cox's paper?
Yes, that was Cochrane and Cox.
Cochran and Cox, yeah. So it's a famous example from the 1950s.
And the cake baking was conducted in 1933 in Iowa State College.
It's a little esoteric, but it wasn't gamma likelihood.
Yes, that's what I need.
I mean, in terms, if you're looking for real valued derivatives or integrals, why not look at Gaussian likelihood? I mean, right?
Gaussian, indeed, you can also generalize these theorems to Gaussian likelihoods, but you must assume that the mean parameter, the mu, is known. Like you can't do the same tricks to mu, but you can do the same tricks to sigma squared.
That can be arranged.
So that the mean is known, but the variances are not.
Yeah.
Yes. So,
I mean, simple example. In this case, I mean, you could, instead of your luminosity function and being as a function of counts in real space, you could take the log normal Gaussian.
You just made the log normal.
Normal and log, right?
Yeah, so exponentiated and then we use a normal. Yeah. So I mean, the scale parameter is kind of special. So that's what's happening here too, that the scale, the gamma parameter, the beta parameter, the scale parameter is fine, alpha is tricky. So for the normal distribution, if mu is unknown, it's not just a fractional derivative, it's you just can't write it down. You don't have an expression.
Yeah, most of the time, yes, it can be hard to.
For me, the mean of a
fractional
normal, is it a most of the time or?
Sorry, for mean to be normal.
No, the normal mean.
The normal mean.
You said most of the time it doesn't work?
Oh, I was thinking about Siyang Li's question, sorry. Yes, for the mean parameter of normal, no, it doesn't work.
It just doesn't, yeah.
It just doesn't, yes.
But you could get.
You would.
Go ahead.
Well, there's always a way to make the work now, but this might be just as bad as just doing numeric integration, right? You can always do some kind of Taylor expansion. You get everything to integer, right? Yeah. Just do a Taylor expansion, so then you can play the same trick, but you just have many terms. But maybe there are some savings.
You mean to deal with the alpha in the gamma? You mean?
Because I think that the whole thing is you need this thing to be of this py given theta, right? That expression had to be written in some theta to the integer power.
Yes. Yeah.
Right?
Yes.
But you can always do tail expansion to get the integer power. You just have many terms. Each term will be derivative. You may just get some kind of new expansion of that thing. Now this is neat. This is just one term, but it could be like what I'm getting reminded is when you think of one term, that is just one coefficient of some long tail expansion, right? Just say that's only one
Yes.
coefficient you need it. So if you just look at a bar function, essentially, I think it is, everything to me ties to wavelets. This is essentially is creating some kind of expansion to localize. Just saying in those cases, you only need a one coefficient, but there are other cases it's not needed. You just have multiple coefficients. Anyway, just
Yes.
a thought. Trying to extend this.
I was imagining rather than moment generating functions, there could be some other generating functions, which is not moments, that works for the mean parameter in normal likelihoods. But the moment generating functions, I think it just didn't work well. Yes. So
did you try I guess you probably have. We probably even talked about this before. Did you try the Fourier transform, like the characteristic function?
Unfortunately, I was looking for cases, but I didn't explore it fully because there are also other very interesting directions for me to try as well. So, yeah. Yes. But I could imagine, for example, in the in complex normal likelihoods. But we need to be very cautious when it's multivariate normal likelihoods. But for complex normal likelihoods, yes, there could be, or some other complex likelihoods than this Fourier.
Right. You know what I'm starting wondering? Maybe this is actually leads to a path. Now this might be far-fetched, right? Because I always wondered, we all know that the characteristic function or the Fourier transform completely determines the original function. And we have been operating all Bayes theorem in the original function space, not in the Fourier space. But there's nothing to stop you to think about doing the Bayes theorem, everything in terms of Fourier, right?
Yes.
So,
I mean, indeed, it relates to the concept of transfer functions in electronic engineering. And I can show a formula that states that if you know the higher order, at least for Poisson likelihoods, if you know the general expression of the higher order derivatives of the prior MGF, then you would know the posterior MGF.
I see. So that's quite connected then.
Yes.
Okay.
And it can be easily generalized to other likelihoods as well, not only Poisson, but Poisson is easy. Yes.
I see.
Yeah, and I think that could be a bypass to avoid samplers if I'm lazy sometimes, but
Sampling.
Yes, samplers. Yes, it can. Yes, it can give us the posterior moments directly. So yeah. Okay, so let me try to finish this so I can get there quickly. So yeah, so this is the general theorem for the gamma likelihoods, and indeed, when I tried with integer shape parameters, the result was very close to the to if I try other approaches, for example, the H likelihoods to the same problem. So indeed, for Xiaoli's previous question, yes, the integer shape parameters could work quite well, like the nearest integer.
Well, there's two things, right, for that to work. One is, well, it works for integers, is what you just said. The other thing is if it's actually alpha is 3.5, and you use 3 or 4, how far off are you?
Yes.
That's the real question, right?
Okay. Yes. In that example, it's not very far off. So.
In what example?
In the cake baking example.
So in the cake baking example, so what did you do? So there's the real alpha was you tried different alphas, integer and non-integer?
Yes, the cake baking example. Yes, the one on the left is where I have the H likelihood approaches. That it was non-integer alpha estimates. But the one on the right is where we tried the MGF-based method to compute the maximum marginal likelihoods.
Yeah.
And we assume that the shape parameter takes integers only, so that for the MGF theorems to work. And you can see here, at least in this example, they are not too far off.
So what was this cake baking? And they measured the temperatures and things there?
Yes.
What's the experiment?
Let me go backwards in my
yes,
backwards in my presentation. Okay. So there are 3 recipes for baking cakes and 5 different batches of cake mix. That's so 45 batches in total, and each batch is divided into 6 cakes and baked at 6 different temperatures, and 6 baking temperatures are 10 degrees apart, degrees Celsius apart, and the response is the breaking angle of the cake.
Oh,
if you put the cake on the table and pivot it, pivot half a slab and measure the angle that it brings.
Interesting. I thought that you have a taste. Somebody who will taste the cake. That's a better.
And look, they're worried about durability.
So,
I mean, it's material
science,
science, right?
You put the cake on the side and then what do you do?
Yes, and you pivot it. Put half of this slab.
You hold down part of the cake.
Yes, yes.
You're going to squish the cake, aren't you?
They break.
It's like the angular, it's angular movement. It's not.
You want the cake to be pliable.
Yes, and
fruit cake.
They didn't say.
I guess there's no topping.
Yeah, exactly.
So here we assume the random effect in this example is the replications of the cakes, and the fixed effects are the temperatures, the recipes, and also their interactions. And the H likelihood approach here is described, although the model is slightly different because in the analysis of the same data in some other papers, there were interactions between the replications of the cakes and the other covariates for example, in Li and Nelder 1996, or Li spoke on H likelihoods. But here we just ignored that covariate because it's just overcomplicating the thing, and our main aim is just to compare the previous approach with our approach, and it's.
So wait, so now.
But what are you plotting? Like, how do you know that these two things are the same or similar? What's your measure? You have the left, which is the old way, the right, which is your way, making alpha an integer, and you're saying they're similar. How did you determine that?
These lines are the model fits, and
so you have a distance between the fitted values, or the uncertainties on the parameters, or the posterior distributions are similar.
Well,
or you just looked at the picture and said they look kind of
first
alike.
The pictures look alike, and the second is that we well, at least I probably didn't describe this part in the. I did describe it in the paper that I fitted this H likelihood model using the R package. I forgot the name of that, and I manually calculated the expressions to for these for the maximum marginal likelihood estimates for these coefficients, and which I after my implementation, the calculation, the maximum marginal likelihoods calculation estimates indeed fall inside the confidence intervals of the coefficients from the H likelihood approach. So which at least shows that they are persistent.
You would like them to be, well, it's the same data, so it's a little hard to think about what that means. What you would like is for them to be the same. If you really think I don't know why H likelihood is the gold standard here.
Well,
I mean, it's not the original question is, what is, if you allow alpha to be an integer, only an integer, or if you allow alpha to be a continuous thing, do you get the same answer? Now, what you've done instead, this is a different model, right? H likelihood doesn't integrate over the parameters.
Well, it's also easy. Actually, in this specific case, it's also easy to get the fractional orders. So I mean, I can verify this after if anyone's interested. But yes, I can simply make a plot after this talk that can show that if we treat, regardless of if we treat the shape parameters as integer only or fractional orders allows, then they
Right, so that was the
estimate
original
out.
question Siyang Li asked, and the idea would be if you could somehow bound that difference, but to do that, you'd have to think about the measure of what are you
Yes,
trying to
yes.
bound, right? The posterior or the
Yeah.
estimator or something like that. Might be tricky.
Yes.
But
Yes.
so what was the outcome? What is the best cake?
Which is the best cake?
Best take. It's the best unbreakable
The
cake.
strongest.
But I
That's
just
the-
wanted to comment on the intuition, right? I mean, usually you would rather expect that they're less stiff if they're baked at higher temperature.
Yeah, so that's at higher temperature is more.
Yeah, but this is
sturdy.
not what you see.
Yeah.
Like I would expect them to break earlier. Like I don't know if you bake it
Depends
at
on
like
the-
500,
depends on the
500
mix.
degrees, then you get like this.
Maybe.
No, that's
Depends
what
on
it
the
says.
mix.
Yeah, no, it is.
Baking angle is higher on the right.
It's stiffer, chewier.
So
And
depends
the
on-
higher the temperature, the further you have to bend it to make it break.
Presumably at some point it would go back down, right? If it ends up being very stiff, then
Oh, yeah.
you
Yeah,
probably
no,
wouldn't
that's
be able
right,
to bend
yeah.
it very far. Is that what you were talking about?
This is what I was talking about. Yes.
Yeah.
They would just
If you
break.
take it to the limit, okay. So you would expect like I don't know, that there's
I have no idea what I would
somewhere
expect.
else.
That's the
It'll go down a bit.
physics stuff.
Yes, yeah. I
Yeah,
mean,
yeah.
this is like how you approach the problem as a physicist, right? You check it against your intuition.
But it's,
No.
they're very similar.
Okay, so
I
there's
was
maximum
looking at the
somewhere in there.
numbers. I mean,
Yeah,
they're
it's
little
only
close.
going up to 230 degrees.
Yeah.
Not much, and it's not going warmer.
Yeah, you can, well, it's 230 Celsius, which is pretty high.
Oh, right, sorry. That is.
It's
Yeah,
not-
it's-
yeah,
it's-
so it's pretty
From
high.
basics, this is pretty high. Yeah.
It's
So
not
it all
for
depends.
melting steel, but it's
Yeah, it's nice.
for fusing helium and
Caramelized cake.
Okay. Where was I?
Baking the cake, the test.
I mean,
No,
people in
no,
material science
I went
they
probably
probably
back
do
to
exactly
previous slides,
like
but
these kind of
Oh,
analyses.
there it
Yeah,
is,
exactly.
yeah, this is where you were, okay.
okay, yeah,
So
yeah, but
maybe you
Yeah.
can try to, because time is running
yeah,
out,
get
talk
the
about
most,
the,
most interesting parts. This is one of the highlights that I like to talk. That it's if we combine this result with Twitty's formula, that's what exactly Siyang Li was mentioning. That we can do the Bayes formula on the not frequency domain, but the Laplace domain. I can call it because our theorem goes from the prior density to the marginal density, and Twitty's formula goes says that if we rather than specifying a prior, we can specify the marginal density of the observations, and that's equivalent to stating the prior, and that can give us inference on the posterior. So it's like going from the marginal density to the posterior. So if we combine these two, we can get a root from the prior, just going to the posterior via the likelihood, of course. So if we use the results in the Bradley Efron's paper, we can get that's the posterior cumulant generating function in this form, and if we combine it with our higher order derivatives, it looks like this. That's the posterior moments here for Poisson likelihoods. The posterior moments can be written as the ratio of as the ratio of the higher order moments of the prior moment generating functions.
right, well, you're not, no, that is the moment? Yeah, the moment, okay, yeah.
Yes. So so that if we have the general expression such that that works for general orders of derivatives of the prior MGF, we would automatically have the posterior moment.
And this is
Poisson
for one
likelihoods.
parameter at a time.
Yes.
So
of course.
this would be just, you have a Poisson random variable with a prior, a parameter.
Yes.
There's no hierarchical model here.
Yes, but meanwhile, we can parameterize our model in a single Poisson, like this formula, like this expression here, such that we put everything, all the complications into these matrices and assume that they can have some complicated, but
There's still no hierarchy here, is there?
There is, yes, you are right. There is no hierarchical representation of the model, yes, but it doesn't, which means that it doesn't marginalize out the population parameters altogether.
Yeah.
Yes. it can still marginalize out. It can marginalize out everything in our, like using this parameterization, it can marginalize out everything in our source intensity model except the population mean variance and the proportion of dark sources. That's 3 parameters. So and yes, so it's this matrix representation summarizes all the previous complicated model in a nutshell. And we can combine, particularly, we can combine this parameterization with use this parameterization in this what I call transfer function, because it's indeed a form of transfer function. It relates to it's in the form of the transfer function that appears in electrical engineering. So there's a link there as well. So we can combine these 2 formulas and just get the posterior densities for posterior moments for the population mean variance and the proportion of dark sources together. So yes. And another extension is that we can use the very similar ideas to calculate the evidences of Bayesian models.
Didn't you want to you said about stopping times in the mathematical links?
Yes, that's here. So here, so we imagine that assume that we have a parameter or random time t that's known to Bayesians as prior, that follows an independent distribution. You can imagine that it's an independent alarm that stops that operates independently with respect to the stochastic process, and assume that there's a renewal process, or in particular a Poisson process here, that is stopped once the random alarm sounds. So this is and this is related to likelihoods to Bayesians, and so the marginal distribution would be marginal distribution of the Poisson arrivals here in this random stopping time model would correspond to the evidence, and the posterior would be trying to infer the duration of the random alarm given the number of Poisson arrivals. Now these words might be a bit abstract. I can give you a little example, like saying that imagine that there's a family of bacteria that reproduces in a Poisson process, such that the next generation, generation 1 is born following a Poisson distribution, and generation 2 is born from generation 1 from the duration is an exponential time duration, and so on and so on. But this bacteria family lives on a volcano that once the volcano erupts, all the bacteria die.
But that's your assumption. The bacteria lives through this temperature.
Sometimes they do.
Yes. So which is exactly what I say here. So the prior would correspond to the eruption time of the volcano, and the likelihood is like how many generations this bacteria can reproduce before the next eruption. And so if you are an archaeologist and you can dig for bodies of bacteria in the soil of volcanoes, and then you can try to infer the last time of eruption given how many generations you observe of bacteria. And that's exactly what Bayesian is treating the parameters and the observations, like the parameters are random or have a distribution in the Bayesian framework, and in exact similar way that the random stopping time would have a distribution, random stopping distribution, and until this distribution, something happens. The observations would occur depending on this.
Yeah, but what does that do with moment generating functions?
So this is why. Well, in the random stopping time, there's a P2 called resolvents. That would give us for example, the number of occurrences before a random alarm sounds. and resolvent correspond to Laplace transforms. It's exactly defined as the Laplace transform of some densities here, and it's so which means that, and plus also there has been loads of studies here in this area. At least in one of Cox's previous papers in 1960, there has been some discussions on the how to find the number of renewals in a random gamma length random interval. So which would correspond to, which if I translate to the Bayesian language, that would be how to find the how to statistically marginalize these integrals, marginalize these parameters if our model has a gamma prior. So the random alarm.
So can you make a relationship between, you have a model that has Poisson counts that follow lambda. Lambda follows a gamma distribution.
Yes, so we can marginalize it in two ways.
Yeah.
Not only the likelihood specific way, which was what I described earlier, but also the
What is that for the
price.
volcanoes? That's what I'm asking.
The volcanoes, the eruption time would correspond to a gamma distribution.
Which is what? The prior?
The prior, yes, which is the prior, and then the number of generations.
So in the original problem, there's n observations from that gamma distribution, right? Those are the n lambdas. So
yes,
different sources.
then that would correspond
you have n eruptions of the volcano.
No.
That would not correspond to n families of bacteria on the
So
same.
it's just changed, I see.
Yeah, like if there are, for example, if there are m parameters, then that would correspond to m volcanoes. And if each of the parameters correspond to one observation, that would be one bacteria in each volcano. So
A little confused about what the data are.
Yeah.
the data would be the number of bacteria generations before the volcano eruption.
Yeah, I understood that part.
So but those go, but those, I mean, can you help me understand the relationship to what
That's
we're
what I
trying to
want now.
understand?
No, that's what
Right,
I
because
want
these are not, those generations are not independent.
Do you mean independent with
Each other.
Well, they are assuming independent because
The number
if
in
we assume-
generation 2 does not depend on the number of generation 1? The number of grandchildren
It's-
does not depend on the number of children?
Well, it's assumed to follow a Poisson process, which means that in any disjoint intervals, if even they are adjacent to each other,
Yeah.
they will be independent number.
The number of grandchildren does not depend on the number of children.
Well, no, we always assume
There's
there's only
some sort of
one
conditional
child.
independence.
There's only one child.
As long as
of
there
the
is one
treated as a
bacteria.
group. It's treated as a group.
The population doesn't grow. We don't consider the branchings. No.
Yeah.
There's only one
So how do these
One bacteria.
one bacteria gives birth to another bacteria, gives birth to another bacteria like this.
It's just one generation.
The number of generations, not
Yeah.
the number of bacteria.
Yes.
How do you get that? Where does it? I mean,
The number of generations of
Yeah.
bacteria.
Yeah.
Assume there's like high-tech archaeologists and
It's all made up.
yeah.
So the whole idea
Yes,
of
yes.
this, I'm sorry, am I missing something? The whole idea I thought was this: you're trying to shed some light on why the moment generating function can be used to integrate out to get the marginal distribution.
Yes, this example kind of explains why this is the case from a probabilistic aspect. This is
Because moment
So
generating
how
functions
we
are used in another problem.
well, yes, and resolvent it could be like another even maybe a series of lectures on what resolvents are, but yes, but resolvents are properly defined as the Laplace transform, so that gives you the number of generations before a random alarm sounds. And it's the similar way that the parameter is assumed to be random in Bayesian. So we can integrate out this randomness. We can just marginalize out the a layer of randomness using the Laplace transform. That's what the
So the
resolvent
fact
says.
that you can use this Laplace transform to do a different integral.
It's this. It's essentially the same integral.
Okay, so then we
yes.
need to make the relationships. What's the Poisson distribution? What's the gamma distribution? What are the lambda i's? What are the y i's?
Okay, so
If it's the same integral, all of those things should have an analogous
yes,
thing,
yes,
right?
exactly. For example, the yi, the observed number of counts will be the number of generations
So we have multiple volcanoes.
in one volcano. in one
Yeah, no,
because
but
the
in
time
the real
is
problem,
different.
there's lots of sources, right?
yes. Yeah, well, in this example, then yes, there's a population of volcanoes.
Right.
And
And
if you got to make up an example like this, why can't we just use active regions and flares?
Exactly. Because we know that flares,
We
it
know that
stops.
active regions
It's
occur randomly. We know that flares occur randomly. The active regions come to an end at some point.
It's some, yeah.
that might be a better example, but although I was not aware of the natures of
Well,
this.
yeah, but
Yes.
I think for me the thing is you still have not given the intuition why the derivative.
Right.
And I think you're making the analogy of a thing, but I don't get the intuition here yet. I'm looking for, if you have 10 observations, then you need to do 10 order derivative, right? And so in this case, like, how do you think about this problem to give me aha moment? I say, oh yeah, now I understand why this. I don't think this is mathematical coincidence, right? I think there's something quite deep. The way I'm thinking about a 10th derivative means I need to look at the 10th, Taylor expansion coefficient, This is in a naive way of thinking about, right? So the Gabi's, it's like pinpoint. You need to make a connection about the derivative to, say, the number of, the stopping time or something of that nature. I don't get the intuition yet.
Well, yes, unfortunately, yes, because I still need to dig into the jungle of stochastic processes to I think someone there should have answered, should have explained why, or should have. I mean, similar theorems indeed exists in the stochastic processes, although it's not named the same way that I named them. But so I would need to look into these books and to find the intuition.
Yes. I understand that. But let's try to generate intuition ourselves by looking at the simple case with count 1 and the count 2, right? You always start with this really trivial case. You can just write down all the formulas. You can stare at them,
Yes.
When you stare at them long enough, sometimes the intuition comes, right? Just say, what the hell is going on? Like, if t equal to 1, t equal to 2, you can even write them as like a writing. You can maybe even just write a derivative as like a finite difference, right? From scratch 1, you can see it got to be some change of the rate. So why the change of rate of you actually do a naive thing here. Again, take the moment general function, right? If you do the Taylor expansion on moment general function, then now this is interesting because this is Taylor expanding on t equal to -1. I have to ask, what the hell, why is it expanding on t minus 1? Then that coefficient will be just what you wanted, right? So okay, actually, I'm suggesting following. Do backwards, right? Writing, because you have this expression, like, suppose I Taylor expanding my moment generating function at t equal to -1, all of them, and replace every coefficient by this expression as this integration, right? That should give you a whole expression. Then look at what is that expression tells you.
I see.
Going backwards. You see what I'm saying? You have all this stuff. You see, you even have the y. You even have the y factorial. This looks like Taylor expansion itself has all these factorial, right? So you just maybe once you expand it, you see, oh, that's entirely trivial.
I see. Okay.
Right. This is literally the coefficient of the t's, right? Not the y's. This is the y's coefficient of the Taylor expansion, right?
Yes.
Right. So anyway, I think this is probably going to reverse the engineer to see what these mathematics. I'm quite sure in the end he will look at the expression and say, "Hey, that's obvious," unless God is playing a trick on us, which I don't believe, right?
You never know.
Yeah, we have
never
to
know. Okay, well then we discover something new.
What?
Active regions instead of bacteria.
Yes.
I'll explain the active region data.
Yeah, instead of bacteria and volcanoes. Yeah.
It's now 1:37. We gotta stop.
Yeah. We have this.
I have a meeting to get to it.
Okay.
Well, very interesting, Chef. It has been very inspiring, very puzzling.
Thanks.
Yeah.
And
We baked the
yeah,
cake.
so there's a
Now it's
whole
very delicious. The cake is involved now.
Grauck.
But it comes with bacteria, so I'm not sure if I want to eat them,
No.
there can be a whole family.
Maybe you
of
could
these
make them
theorems.
yeast instead.
Yes, these would
Oh,
be
yeast.
Oh.
That's
Eating
right.
yeast is completely fine.
yeast and then being baked at a random time.
Exactly. Yeah.
And you can generate different yeast, whatever.
Oh, yogurt.
Yogurts.
You could make it Greek yogurt or something.
Active bacteria, active bio. Do you think we can find a time in the next couple of days to talk about what we need to do for him to have a paper?
Right.
To get, I don't know if it's Lazi's paper out or if it has to be a new paper now.
And you should.
Hang on,
Yeah.
let me stop.
Oh, should I stop sharing?
Yeah, you can stop.
Yes.
We can maybe finish the meeting. I say,
Yeah.
thank you to everybody.
Thank
for
you.
coming.
Thanks, everyone.
Well, thank you, Chef.
Yeah.
Thanks, you.